Linear equations can represent financial models. It can represent the force added to a system. It can represent the temperature measured of two different design systems. So when we look at when linear equations or when lines intersect, and when those linear equations represent two different models or two different designs or two different sensors, the point of intersection represents when the advantage of model A over B changes and flips. Now there's an advantage of model B over A. So understanding when and how to identify when lines intersect is really important. That's what we're going to look at in this video. When we have two lines that have the same y-intercept, the point of intersection is the y-intercept, right? So in these three pairs of linear equations, we already know that they're going to intercept at 0b, right? At x equals 0, because that's where the y-axis is, and at y equals b, where b is the y-intercept. So in this case, it's going to, the red and blue line here are going to intercept at 0, 3. The red and blue line here are going to intercept at 0, -1, and the red and blue equations here are going to, our lines here are going to intersect at 0, -4. But this is a good place to start because we can solve for it in a general way and see that the method works because we already know what the final solution is. So what we're going to do is first recognize that the intersection point is a common point. And so we're going to call this common point x1, y1. And what we're going to do is plug in x1, y1 to both of these equations, and then we'll solve for x1, y1. All right, so let's start with this left pair here. So I plug in x1, y1, get y1 equals 5x1 plus 3, and y1 equals 2x1 plus 3. So for it to be a common point, x1 and y1, whether it's in red or blue text, have to be the same values. So I can equate the y1 values, and then I have 5x1 plus 3 is equal to 2x1 plus 3, right? Just equating the right sides of these, the original equation. Then I solve for x1. Well, if I subtract 3 from both sides, because they share the same y-intercept, that's going to go to 0, and then I'm just going to have an x1 term. So I have 3x1 equals 0. The only way this can be true is if x1 equals 0. That's not a surprise. We expect it to show up we expect x1 to be equal to 0 because that's where it intercepts. If I plug in x1 equals 0 into either the red or blue equation, I get y1 equals 3, right? And so that means the line intersects at the y-intercept. Same thing would be true for these two here, so we'll quickly go through these as well. Plug in x1, y1 for both equations, equate the y1 terms, then I only have x1 terms. Solve for the x1 terms by isolating the x1 on one side, the constants on the other side. Because the y-intercepts are the same, they're going to drop out and equate to 0. So same as this pair over here. Our x1 hazard equals 0, which represents the y-axis. Plug in x1 equals 0 into either the red or blue equations here. We get our y-intercept, y1 equals -1. So that shows up. The intersection point is at 0, -1, or the y-intercept. Do the same thing on this last example. Plug in y1, x1, equate our y1 terms, solve for x1. We see that x1 equals 0. Plug in x1 into our original equations. We'll get our y-intercepts. So really easy to solve for the intersection point if the two equations have the same y-intercept. And we could see in a graphical form, right? So this pair of equations intercept right there, this pair intercept right there, and this pair right there, all of which all three pairs intercept along the y-axis because they share the same y-intercept. Now, we can take a look at what happens before and after the intersection, right? So after the intersection from this pair, the line with the larger slope is larger for the rest of the time. Below the intersection point, the line with the smaller slope has a larger value in any x location, right? So the y value is larger for any x location. Let's see if it's true here. After the blue line, after the intersection point, the blue line's higher. Blue slope is 7, the red slope is 3. So that's consistent here. Let's take a look at this term here. Here we have different signs. Let's see if that matters. So after the intersection point, the red line is higher than the blue line. The red slope is 2. The blue slope is -1/2. So it's still consistent there. So this shows how important it is to recognize when you have an intersection point, because the y value of the equation that has a larger y value depends on if it's before or after the intersection point. Okay, so now we've seen how to solve for the intersection point for a very simple case where we have two lines with a common y-intercept. What happens when we don't have that? Well, the steps to take are pretty much the same, except we're not going to solve for the y-intercept, and we're not going to solve for an x1 value of 0. So here we have 5 example problems. In each example problem, we have 2 equations. Each equation we're going to solve, or for these equations, we're going to try to solve for the intersection point. And so the steps we're going to take are the same as what we did earlier. So first we say, we give a dummy point x1, y1, right? So use a subscript 1 to represent the point of intersection. We plug in x1, y1 into our pair of equations, and then equate. We equate our y1 terms so that we're left with just x1 and constants. And in that form, we can solve for x1. Once we solve for x1, we can plug in x1 into either equation 1 or 2 and solve for y1. Now, sometimes it's a good check to plug in, once we solve for x1, plug in both to equation 1 and to 2. And if you don't get the same y1 value, then you did some math wrong, or the calculator mistake. Because by definition, the whole process is meant so you can plug in x1 into either of them, or you can plug in y1 into either, and you should get the same x1 or y1 back, right? That's the only way that it represents a common point. So let's take a look at each of these 5 example problems. We'll walk through each of these steps, and then we'll show you the graph to show you that the point of intersection that we find actually matches what we see in the graphical form too. Okay, so equation 1 is 2x plus 10. Equation 2 is 2x plus 6. So remember what our first step is? First step is to let our intersection point be some dummy x1, y1. Now what's the second step? The second step is to plug in x1, y1 into both of these equations. So let's do that. So it looks the same as the equation, but we just put subscript 1s next to them. Now the next step is to equate the y1 values. So I say y1 equals y1. So 2x1 plus 10 is equal to 2x1 plus 6. That's what I have here. And now we need to solve for x1, right? So I can move this to this side. And I'll say this will show up as 0 is equal to 6. And that doesn't make sense. You can't have that happen. So what's gone wrong with this problem? Well, the y-intercepts are different, but one thing that is the same is the slopes. And so if you remember from previous videos, we should say that when we have the same slope, the lines will be parallel because they're growing or descending at the same rate. So they'll never intersect. So we can show this in graphical form as well. Here's equation 1. Here's equation 2, right? We see them intersect at 6 for the blue equation and at 10 for the red equation. These lines will never intersect. They're offset by a value of 4, which we see as 10 minus 6, and they will always be offset. So this was kind of a trick question because these lines will never intersect, but it's good to know and recognize that. Okay, let's take a look at a more conventional problem. Here we can check again before starting. Our slope is 1, our slope is 2. All right, so we know these lines will definitely intersect. We just need to figure out where. So we start by saying that we have a dummy point x1, y1 where they intersect. Plug in x1, y1 to both equation 1 and 2. Equate the y1 values of both equations. And then we'll get x1 plus 3 is equal to 2x1 plus 4. Now we can solve for x1. right? I'll move all the x1 terms to one side, all the constant terms to the other side. So a negative 4 is added to both sides. So negative 4 plus 3 gives us negative 1. A negative x1 is added to both sides. A 2x1 minus 1x1 gives us x1. So the point of intersection is x1 is equal to negative 1. Now I need to find what y1 is equal to. So I plug in x1 equals negative 1 into either of these equations, I can solve for it. So I'll do it for both, just do a check, right? So let's say I do it for the equation 1, negative 1 gets plugged in there. So negative 1 plus 3, that gives us 2. So I plug in negative 1 into this, the blue equation, I get 2 times negative 1, that gives us negative 2, plus 4 minus 2 is 2. So it matches. So my y1 term is equal to 2. So the point of intersection is 1, 2. So we can take a look at the graph to see if that's consistent. So here's my equation 2 in blue, and here in red is my equation 1, x plus 3. And so we see a point of intersection here, that's at negative 1, and 1, 2, that's at y equals 2. So it matches what we expect to see. So there's a lot of different online calculators that you can use if you don't have a graph calculator, but I strongly recommend you either get a graph calculator or pull out or open up the online graph calculator. It's very useful to, after you solve some of these problems, to take a look at the graph to see if you match the intersection point. So each of the next set of examples are basically the same process. So I'll go through them a little quicker, and you can slow down and pause the video if any parts are a bit confusing. But here again, we have two equations, different slopes, so I know that they're going to intersect. First step to find the intersection point is to define x1, y1, and then plug it into both equation 1 and 2. So that's what we do. And then what's the next step? The next step is to equate both y1 terms. So we get negative x1 minus 2 is equal to negative 4x1 minus 5. And now we solve for x1. So the variety of ways to do this, I move negative 4x1 to the left, I get 3x1. I move the negative 2 to the right, I get a negative 3. So x1 is equal to negative 1 in this case. Then we could plug it into either equation 1 or 2, doesn't matter. You plug in your x1 term of negative 1 there. So I'll just look at it from the red equation. I've got negative 1, that gives us positive 1. Positive 1 minus 2 gives us negative 2, or sorry, negative 1. So same thing with the blue equation, just plugging in x1 equals negative 1. So I know my point of intersection is negative 1, and I can take a look at the graph to see if we're consistent. And there we have our intersection point, negative 1 for x and negative 1 for y. Right? So we see the process is relatively straightforward. You don't need to build out you could build out an x1 or y1 equation using variable form, but there's no real need, right? It's actually pretty useful to walk through the process in each problem to make sure that you understand the concepts and that you're actually just using the general form of the linear equation to start with. I hope you're getting the hang of it at this point. So let's take a look at this set of equations. Pause the video, see if you can work it out on your own first, and then think about after the point of intersection. So x value is larger than the point of intersection. Do you expect equation 1 to have a larger y value, or do you expect equation 2 to have a larger value? Pause it, work it out for a couple minutes, and then replay this video or continue this video to see if you are matching what answer I get. Okay, so again, we're gonna go x1, y1 for the point of intersection, plug it into the equation 1 and 2. And then we equate both sides here. So we get negative 3x1 plus 2, negative 2x1 plus 6. And then we solve for x1, right? So move x1 to one side, move the constants to the other side. So I added 3x1 to both sides, I get an x1 term. I subtract 6 on both sides, I get a negative 4 term. Okay. Then I plug in x1 to these to both equations just to check, but I'll just do it for the blue equation this time. So I get negative 2 times x1, negative 4, gives us positive 8, plus 6 8 plus 6 gives us 14. So my intersection point is -4, 14. Now I'm looking at these. Which equation has the larger slope? Well, they're both negative, so -2 is larger than -3. So after the intersection point, I expect the blue line to be above the red line. Let's see if we're consistent with that. So there's my point of intersection, 14. After the point of intersection, the blue line is above the red line. So it's consistent with what we talked about earlier. What does this mean? So they have you could think of the intersection point as a common starting point. After this point, the blue line is declining at a slower rate than the red line is. So it's always going to be above the red line at any common x location. Okay, and this is the last example problem we'll work on together. Again, so just to give yourself some practice, pause this video, try to work this one out, and again, think after the point of intersection, do you expect equation 1 to be larger, or do you expect equation 2 to be larger? Okay, we're going to go through the same process again. We're going to have x1, y1 represent our intersection point. We'll plug x1, y1 into both equations, and then we equate the two equations. So we get 3x1 plus 1 is equal to 2x1 plus 2, and solve for x1. What did you get for x1? I get subtract 2x1 from both sides, and I subtract 1 from both sides. So I get x1 equals 1. Then what do? Well, then we plug 1 into either of the two equations up here, and we get 3 times 1, which is our x1 term. 3 plus 1 equals 4. So my y1 term is equal to 4. Did you get an intersection point of 1, 4? If so, great. There's no tricks other than the type of problems that I've shown you for linear equation intersections. These are all the different types. Okay, so before we show you the graph, which one do you think will be larger? Which equation is going to have a larger y value after the point of intersection? So remember, all we do is we look at the slopes and compare the slopes. So equation 1 has a slope of 3, equation 2 has a slope of 2. So after the point of intersection, I expect equation 1, because it has a larger slope, to be larger. So there's my point of intersection. Larger values are showing up in equation 1, right? So why is that the case? So again, point of intersection is like a common point. As you move to the right, so that's a common point. And as you move to the right, as x grows, right, the red line is growing at a faster rate because the slope represents a rate term than the blue line. So it makes sense that the larger slope is going to have a larger value.